Good morning, ladies and gentlemen. Today we're going to be looking at some hot plates. So they needed repair. These IKAs, they come apart with taking out that screw. You don't need to take out the motor screws. And then you take off the rubber leg, and underneath there's a screw here and here, and it comes apart. So I got these off of eBay as parts only, and what I need to do to fix them, well, a number of them, you simply have to put this jumper, it's a piece of solder, because they were missing this little plug you put in the back. See if I can find it. Can't seem to find it. Alright, that's a simple fix. Now, some of these use solid state relays inside to do the heater control, but most of them were using a little relay. Now, this is not the exact replacement, but it had mostly the same pinout. I had to fold down one or two of the pins, but it actually worked just soldering it into the hole pattern. Yeah, the contacts just get worn, and it stops warming up the hot plate. Others had errors where these switches needed of course you should take it apart to get at it, but you can take by wedging in a knife-like object, you can scooch out the switching element and then take out the little pieces. Now, one piece is like that shape, and right there at the center where it rocks had built up corrosion. Also clean one side has points, where the points, so I cleaned that by scratching on it with sandpaper or something like that, or actually a razor blade, X-Acto blade. Then I sprayed some WD-40 out of superstition that might help. Yeah, that was all that was wrong with this batch of 6 hot plates. Here's some notes. This is a relay version, and I WD-40'd. I didn't even take it apart. I just WD-40'd it and then put the jumper in the back. This is for an external temperature probe, and so without this jumper, it's thinking there's no probe, so it won't turn the heater on. Alright, it's an older version of the IKA. Now, the confusing thing is it calls it an IKA RCT BASIC, and the control knobs, yeah, they got it calibrated in temperature. Here they don't calibrate the RPMs. Yeah, you'd probably have to double check that actual temperature you're getting. Now, these are also from eBay. This is where you can put on little test tubes in there to get them all, and you can also put a baby tiny magnetic stir bar. This is what a stir bar looks like. Stir bars. Those are pretty big for these test tube size one. They have them even tinier. And the nice thing about the IKA brand is it's got a lot of torque. What the heck, I'll plug one in. What's the use of making a video if they're not plugged in, eh? I could just be telling you they're fixed and they're not really fixed. Let's plug this one in. Alright, so you know the IKA's alive because they turned on the computer brain, turned on the LED. Now when it's green, alright, also you can select whether you want it on or off. Let's turn it off. Yep, the light went off. Light came on. The interesting, nice thing about this, when you crank up the heat, it turns red. Red not telling you that it's hot, but telling you it's not warmed up to your set point yet. That's getting hot quickly. We don't need to heat it, so let's turn it back down. We can actually turn it off on the heat. And we'll spin it. Yeah, you see that? Nice little hot plate. So what I was saying is, let me unplug this. The IKA brand. Alright, so that's the older style. The newer style, single, I think it's one of those 6-sided things. Single screw to the middle lets you separate the case. Alright, let's see what this is going on. This is the current one under surgery. Now this takes a quantum leap. Well, I don't know. So here's the circuit board for that. This one was sold. Alright. So anyways, these teeny weeny parts are best looked at under the microscope. Let's see if we can see anything. Alright, sorry about that. Alright, let me tell you which parts got discovered to be burned out. See if I can find them. Alright, that particular eight-legged bug is your driver, and there's 3 of them because it's 3-phase. Now those two on the very left there, those 2 legs, one's the source, the other's the gate to control it. Anyways, that alright, you can't tell anything. Now, by an arduous process of sketching this out and using a ohm meter, double-sided circuit board. So when it dived to the other side, it will have these like baby grommets that go all the way through. And by you know, with all this coronavirus stuff, I'm the only person here at work, so I got all the time in the world to play around with this. This is what boredom gets you in education in electronics. You can sketch out, you can sketch it out, the circuit. Alright, this goes off to your motor. There's your 3-phase, at least by studying. Let me get my pencil. I always drop my pencil. This is your 3-phase motor And it's designed properly, this made in Germany stuff. It gives you good torque and good speed control to spin those little stir bars. Now let's take a look at a half-assed design job. Here they're using a motor that was intended to run at a single speed, and they're using like a light dimmer, one of the two, to control its speed. Well, you can't get much torque that way and control the speed in any decent fashion. Also, maybe not this model, but some other model manufacturers, when they're trying to speed control a motor that's really intended to just run at one speed, the windings develop shorts. Maybe they exceed the voltage, and they, you know, with those voltage spikes, if you're shutting on and off the current, and the winding gets shorted out, and that's the end of that hot plate. Because I don't think you can easily find, maybe you can, but I could not find other motors to just like buy. Cheap shit design. As opposed to IKA digital. Alright, let's plug it in to see if the computer, I believe that's the computer brain right there. I think it was Cypress Semiconductor. I'm not sure. Let's plug this baby in. Let's make sure I'm not endangering myself. Oh yeah, disclaimer, educational purposes only. Don't do this because you got to have electronics common sense. If I touch the fuse area, I'm going to get a deadly shock. Alright, let's see. Look at that. Let me turn off this light here. If this thing has the brains enough to say it's flashing an error message, that means your computer brain is alive. Some other things you can poke around at, you know, I'm saying for educational purposes only, you have to know how to poke around independently. You have to know how to poke around on your circuit without shorting out, you know, if your probe, so one attempt to keep your probe, that's a bare probe. That can short stuff out a little more easily. And if you heat shrink some, that is a little bit less prone to shorting out. Still, that tip, I guess you could get the heat shrink to get just all but the teeniest, tiniest tip. But when you do that, then the thickness of the insulation will then prevent you from getting right down in there on these surface mount device stuff. Some other, alright, let me just unplug this. It looks pretty daunting from a repair person's standpoint to see all these wires. Yep, they go through this connection, go into your motor. 8 wires. In the old days you had 2 wires to drive a motor. But then after you're meditating on it for days on end, it becomes less of a daunting challenge. Let me try to describe to you these pins that you discover by, oh, these pins are for your pt100 or pt1000. They got a double, they got 2 of them to detect the temperature in a hot plate. Here they are. So platinum resistor, they either go with the 100, that's the most common. I think these may have been 1,000. So 1,000 ohms at somewhere around room temperature or the freezing point of ice, I forget which. And there's your heater element. You can test the resistance of that. I think it's 20 ohms or so. See if that was bad. But it was good. Well-made hot plate. IKA, made in Germany. Right, I don't work for IKA, but I should. So these are those rotary, you can spin them forever, they're not going to come to a stop. They put out those, one voltage goes up, then the next, and the next drops, and the next drops. That sequence of events tells you whether they're going forward or backwards. They got a name slipped my mind right now. Optical rotary switch, but they're not optical. They're a rotary switch of some kind, and I forget what they call that signal where they ding, 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 ding. I should, okay. Alright, you can test the voltage. This is related to your, right there next to your drive circuitry. So this thing is your power supply module. It was faithfully putting out voltages, so great. It's not something you gotta fix. Now in the design of this circuitry, you got 45, you look at that 100 volt rated capacitor. This black thing tells you that's your negative, I'm pretty sure. I sometimes am prone to getting things backwards. So if you measured there, you get a nice clean 45 volts. This one was 12 volts. If you measure one side to the other, this supplies the power to the Hall effect sensors. So I forget which, but one of these is ground and one of these is 12 volts. One of at these pins going out to your motor. And the next three are 3 Hall effect sensors, so that's going to be coming back with either a 5 volt or a 0 volt as you spin your motor. So all of that was faithfully working. Now what was not working was the power to, okay, let's go through these pins. 3-phase, 1, 2, 3, those are actually the amps and volts, high power going out to your motor. Then 3 more for 3 Hall effect sensors. Wait. 1, 2, 3, 1, 2, 3, and then 1, 2, 3, huh? Alright, so one of those 9-pin connector, but one is 1, 2, 3, 1, 2, 3. Okay, not sure. But I can identify, so I might have sketched something wrong. This one goes to one motor driver, this one goes to one motor driver, and then the third motor driver. Now this is connected to pin 41 on that CPU, then pin 8, and then pin 40. Those are your 3 Hall effect sensor outputting coming from the motor. Then you got this pin. Then you got your 12 volts. So I actually forgot to draw in a pin. I only have 8 pins, it should be 9. So somewhere in there you got a not connected on the actual thing. One of those is not connected. I forgot to actually draw it here. Alright, let me just quit mumbling. I guess I can't quit mumbling, but alright, so when you look at that on the microscope, you can get these parts with labeling on them, and you can't actually look that number up directly. Okay, so what you do is you search on YouTube SMD part labeling, and then it'll tell you how to go to a website where it's like one of those charts where you first on a vertical column you look up the 6, on the horizontal column you use up the C, and then from there you can click on it, and then you go to another page where you can look through 6C what, and you find the 6CW down a big list, and then it'll finally tell you what the part is, part number, and you can go to a data sheet. So what kind of parts did we find? Alright, well, let me just tell you, okay, this is your driver. It's got two high power MOSFET. You got an N type and a P type. And then the outputs in this design here, they're connecting the N type output and the P type output together, which means your control circuitry better not turn them both on at the same time. Otherwise, you're going to be connecting the negative side to the positive side, and you're going to have a straight up short. Now they got three of these. They're kind of like open circuit at low voltage. It's probably some motor protection. It's going from one side of the coil inside the motor to ground. Alright, so this thing was dead. This particular chip was burned out because the source and gate are not separated anymore. If it's a good chip, you should not have any conduction between those two, but this one you do. Now, this design is pretty good because once that's shorted, well, somehow it caused 45 volts to appear, and it would try to, now there it's, okay, this whole circuit is controlled by two lines from your computer, and it's a 0 or 5 volt signal. So a 0 or 5 volt signal, obviously, if you look at the data sheet, 5 volts will make it conductive to a good on the N side to allow it to conduct 3 or 4 amps through it without causing trouble. So there you go, straight up 5 volts here. Then they got okay, this is a 3-pin little surface mount device, but only 2 pins. It's just a diode inside. I'm pretty sure it's just for some kind of protection so you don't shoot negative voltage back into the computer. It takes it off into ground. Okay, one input or one output from the computer, pin 29, and then you got your other side, your gate on the positive side, going through a single transistor, NPN. So notice how transistors are like two diodes. I mean, at least for when you test them. So they're from here to here. It behaves like a diode. So N, P, N. Yep, that's the gate. That's the base. That's your emitter, the bottom of your transistor. Pin 7. So I measured it. Pin 7 was putting out at one, obviously this could change, but when it was all disconnected and flashing the error message, pin 7 was putting out 5 volts on all three of the drivers, 5 volts and 5 volts. And the other side, the negative side, was putting out 0 volts, 0 volts, and 0 volts, which basically keeps all of these off. Now, a very intriguing learning experience I had was how in the world can a 5 volt signal, okay, so when you got your P-type MOSFET here, you got the source being fed 45 volts. The gate, in order to turn that on, or to keep it off, has to stay at 45 volts, Which, okay, I drew a no-no. I drew my wire inside the, when I sketched the circuit, I drew this wire. It's actually inside my little schematic box of the chip. Well, anyways, okay, it's probably not the best etiquette. So you see the 2K resistor plus the capacitor keeps, if all things were not otherwise not connected, it keeps the source, I guess that's SP, source for the positive P-type MOSFET, and then there's your output. That would be your drain. I guess that's an attempt at a D there. Here, see, that's another D, and another D, and a D for the N-type, and a drain for the P-type. And the chip puts out 2 lines for the output because, you're dealing with 4 amps controlled by that little baby chip. Alright, how in the world can 5 volts going to 0 volts back to 5 volts control that? amazing discussion here. Let's see where I discussed it. Did I discuss it on the page over here? No. I think I discussed it on this one. Alright, that's just a pinout of it's the chip. Okay, this is built around 2010. So when I was exploring this circuit, I started to get into other things that seemed to share wires, but then I realized it was for some other aspect of it, because the wires it shared turned out to simply be 5 volts, a 5-volt line and ground lines. So I stopped trying to figure out what that all did, because it probably was not broken. And also, I'm kind of ain't the smartest chip on the block. Alright, with my remaining few minutes here before this Gilligan's Isle, I can't believe they could put a whole Gilligan's Isle show. Alright, I guess I'll have to, boys and girls, you're lucky today. Gonna have to start from scratch. Oh boy, can I start from scratch? Am I that smart? I guess I'll have to be. Alright, so we'll notice we got the 5-volt going through a 475, let's round that up to 500 ohm resistor, going into a transistor. Alright, let's get that sketched out. What my luck, I'll have to use a pen today. Here, classic picture of a transistor. NPN rated at 55 volts or something. That's your emitter, your base, and your collector. So the function of a transistor is if you get a wee bit of, and these are all like a diode type voltage drop. So I found it in the circuit, it's pegged, this base is pegged because it's directly attached to the 5-volt power supply. Then you got your resistor going to your computer pin, which could be either 0 volts or 5 volts. Let's see what happens when we're plowing 5 volts here. So then you got 5 volts here and 5 volts here and a 0.6 volt barrier. No current flows. That's gonna be how you shut things off. Now let's go up top here. Up top you have, alright, there's your transistor I was just talking about. There's your gate input. You got a 2K resistor and some kind of tiny, maybe a 0.01 or 0.1 microfarad capacitor, or even less. I have not read that one yet. But, okay. So let's just focus on putting a resistor there. And then that's tied to the 45 volts power supply. And then to drive the gate, you're pulling it off right there. So this is going to go off and drive the gate of your power MOSFET, the P-type power MOSFET. So P-type, a gate with the P-type. And then this has to go, okay, so 5 volts is adequate to drive the N-type. However, P-type MOSFETs have a higher resistance, and it is suggested to drive them at 10 volts, and the max ratings for the power MOSFET was even 20 volts. Okay, can we get that kind of thing? Can we get, like, let's see, 45 minus 10 would be 35 volts here, or minus 20. You can get 25 volts here. All right, let's turn it to 0 here. So we're going to turn it to 0, and that means current's going to flow through that, and you can get your voltage drop. So this would be, let's say, about 0.6 or 0.7. So let's call that 4.3. You know, as just a fundamental rule of a transistor. If you got 5 volts here, all right, guess what? I'm going to have to stop this and go to part 2. Sorry, folks. See you at part 2.